In this class, we initiate the discussion on the chapter titled Electron Dynamics and CRO. The main objective of this unit is to give you the complete details of CRO, which is expanded as cathode ray oscilloscope, and to give you the details of how charged particles will move in the heart of the CRO, that is CRT. In fact, you have both electrostatic field and magnetostatic fields present in various types of CRTs. For example, if you consider the basic CRO which we are using in our laboratory, we use only electrostatic deflection there. Whereas if you consider the cathode ray tube which is used in televisions, then there they use magnetostatic fields. So to begin this unit, it is essential to identify the motion of the charged particles under the influence of each of these fields. That means electrostatic field and magnetostatic fields. So first of all, we have to define what is an electric field and what is a magnetic field, and how particles behave in each of these fields. If you consider the charged particle which is present in an area, in a region where there is no field at all, then you can assume that it doesn't contain any velocity. It is stable, it is constant. On the other hand, if it enters into the region where there is electrostatic field, some of the effects we can predict are either its path will be altered, that means it may be deviated from the straight line path, or sometimes it takes circular path, sometimes it takes helical path, sometimes it takes the path of parabola. Okay, so under what conditions actually a charged particle diverts its path from the straight line to different types are to be studied in this chapter. For having the clear idea, we first consider the motion of the charged particle in an electrostatic field. As I said now, the electrostatic field means we place the charged particle in an electric field. So the definition of electric field and the units of electric fields are volts per meter. That means you can expect this electric field imposes a force on the charged particle. Because of this force, the path of this electron will be diverted. And when you consider the motion of the charged particle under the influence of an electrostatic field, then we can give the expression for its force, that is given in the next slide. The force on a positive charge Q in an electric field of intensity E is given by Q into E, the resulting force being in the direction of electric field. So we can express this as GHQ is equal to Q into E, where GHQ is in newtons and Q is in coulombs, E is in volts per meter. So the previous slide gives you the expression for the force exerted by the electric field on the charged particle. Now if you want to find out the motion of the charged particle under the influence of this force, we have to consider the Newton's second law. It says, so we are once again taking here the Newton's second law as the reference, and we are equating the Newton's second law with the force exerted by the electric field, that is FQ is equal to Q into E, which is equal to MA, and equated to M into dV by dt. Here M is mass, which is expressed in kilograms, A is acceleration in meters per second square, and v is velocity, that is meters per second. In the above expression you have seen ma is equated to m into dv by dt, because a stands for acceleration, which is nothing but differentiation of velocity with time, so that is given as dv by dt here. The solution of the previous equation can be obtained by considering the initial conditions. So first of all we have to identify what are the initial conditions. In order to judge the initial conditions, we have to simulate the conditions of keeping a charged particle under the influence of electrostatic fields. Okay, so here we create two plates which are charged by the external field, and between these two plates you can identify the presence of electric field, and we allow the charged particle to move into this electric field, and we also consider the force exerted by this electric field in all the three axial dimensions, that is x, y and z. We assume that the charged particle is moving along the x direction and the field is along the y direction. Okay, and as the force and the movement of the electron is in x and y direction, you cannot expect any momentum of the charged particle in the z direction. So based on this you can develop the initial conditions. Before that I will show you the simulation of the situation of keeping a charged particle under the influence of electric field in this figure. You are looking at this slide containing the motion of the particle and also its path under the influence of the field. For example, you can consider it as similar to the arrangement of a parallel plate capacitor. To simulate the presence of parallel plate capacitor, I have put here two plates which are in parallel along the x direction, and these two plates will be energized to create the electric field, and the motion of the electron is indicated with a arrow at 0, that is along the x direction, and the distance or the separation between these plates here is given as dl, and force is acting in the negative y direction as indicated by E here, and the length of the deflection plates is shown as capital L, and the motion of the particle under the influence of this electric field is shown with a dotted line and indicated here as Vd. Now we will give the initial conditions, we will develop the initial conditions based on this figure. In the figure shown previously, you can easily identify that electron doesn't contain any motion in the z direction, and when you take its location initially at x is equal to 0, y is equal to 0, z is equal to 0, we can express its velocities as initial conditions as given in the following slide. So the initial conditions are, in the x direction we say its velocity as vx, that is equal to vax, and x is equal to 0, and in the y direction vy is equal to 0, that means we are not expecting any velocity in the y direction, so y is equal to 0. Similarly in the z direction also we are not expecting any velocity. So ultimately this slide gives you the information about the initial conditions for identifying the velocity of the electron. So from the previous slide you can identify that there is no force on the particle in the z direction, so it do not move at all in the z direction, so the whole motion of the particle will be confined to the xy plane, that is the plane of the screen you are viewing the TV. That means the carrier will always move on the plane containing the screen of the TV.